Hi, thanks for coming. In this video, I'm going to explain what the resonance graphs is all about. So we are going to use a spring mass system as an example. There are two ways to set the mass into oscillation. One way is to simply displace it from its equilibrium position, like I come along and I stretch the spring down, pull it down, and then I let go. When I do that, this guy is going to be in oscillation. This is what we call a free oscillation. A second way is to force this guy into oscillation through another oscillation here. So we connect the mass and the spring to a vibrator here, which is connected to a signal generator. So we can control the frequency at which the vibrator is vibrating. So depending on the frequency of the driver, the forced oscillation is going to attain different amplitude of oscillation. So this what the resonance graph is all about. It's trying to plot the different amplitude attained by the forced oscillation at different frequency of the driver, the so-called periodic driving force. Let's start with a very low frequency of driving. So imagine that this guy is doing left, right at say one oscillation every 2 hours. When you do that, then this mass is also going to do an oscillation at a frequency of one cycle every 2 hours. So basically this guy is going to be exactly in line with whatever the vibrator is doing. And because the amplitude of the vibration is very small, the forced oscillation's amplitude is also going to be small. So that's why the resonance graph always start off with a low amplitude at low frequency. In fact, this amplitude is exactly equals to the amplitude of the driver. Technically, we should put a bubble here because it's meaningless to talk about a periodic driving force that has a frequency of 0 Hz. So we mean a very low frequency, but maybe not 0 Hz. Alright? Now, let's imagine that this vibrator is now driving at very high frequency. When this vibration is very fast, there's practically no time for this mass to react. So you just see the spring stretch and unstretch and stretch and unstretch at very high frequency. Say 2000 Hz for in the vibration, and therefore this spring you just see it stretching and unstretching also at 2000 Hz. But the mass here is going to be practically motionless because it just has no time to react to this very fast changing driving force. That's why on the resonance graph, when you are going towards high frequency, the amplitude of the forced oscillation actually approaches 0. And so something magical happens in the middle. This guy has a natural frequency, like if you replace it, it's going to do its own oscillation. If this vibrator is driving this guy at the same frequency as this guy's natural frequency, then you see that the energy is going to be fed continuously into the spring mass system here. You see the amplitude grow and grow and grow and grow because it's so efficient at this frequency for energy to be fed into the oscillation. And that explains the resonance peak. And the resonance occurs when the frequency of the vibrator or the frequency of the driving force matches the natural frequency of the system itself. Okay, that's all. Ta-ta!